Now, up to this point, we've covered differentiating simple equations. So we've differentiated simple terms, we've differentiated combinations of terms, so a linear function that's written out term by term. We've covered roots, we've covered powers, we've covered negative powers. We're going to look at one more type of complex linear differentiation. That's for differentiating slightly more complex linear functions. And this all extends from trying to make taking the derivative of a much simpler function a bit easier. So imagine I want to take the derivative of f of x when f of x equals x plus 1 squared. Now, we've covered how to do this at this point. What we do is we multiply out the brackets, we get each term written on its own, and then we take the derivative. So let's do that just now to do it. So multiplying out the brackets, we get x squared plus 2x plus 1. We then want to take the derivative f dashed of x and take the derivative of each term all on its own. So if I take the derivative of the first term, I get 2x. Derivative of the second term, I get 2. And then this one just disappears. Now there's a common factor of 2 here, so let's take that out. So 2 bracket x plus 1. Now, that's a couple of lines of work in. There is actually a quick, easy cheat way. I could have jumped straight from there to there. Look at how these look. This one here, x plus 1, that is the same inside the bracket. It's got a power of 2 here and a coefficient of 2 here in the front. So it almost looks like I can just take the power in the front down and work with that. But actually, it's nearly there. There is one extra little trick we have to imagine. Because what we can imagine is we have just a generic function that's ax plus b, and we put it to a power of n. This kind of follows the same routine. The only difference being is that a is 1 and so is b. I've taken the derivative here and I've got to this point. What I'm able to do is I'm able to generalize it and say taking the derivative of this in general gives me an bracket ax plus b to the power of n minus 1. So I've done everything here that I said. So I've brought the power down, n's down, taken 1 off because 2's gone to 1. The only difference is there's no a multiplication out here. But actually there is, because a is 1. The coefficient of the x value here is 1. So we have actually done the exact same thing. And this is a nice, quick way of doing this sort of question. Differentiating something of this form, this is the quick way of doing it, to save us having to multiply out the brackets and muck about with each term all on their own. So let's have a look at that. So imagine I give you y equals 5x plus 2 all to the power of 3. So imagine I've got that 5x plus 2 to the power of 3. We can actually use that same functional form to get the derivative of this. Now what did we do? We brought the power down, reduced it by 1, and then multiplied it by the value of a. So we bring the power down, keep the bracket the exact same, 5x plus 2, reduce the power by 1, so that becomes a 2, and we times the whole thing by a. Remember, a is the coefficient of the x part. So there is your a there, so we times it by 5. And then it's a case of simplifying. So we get 15 bracket 5x plus 2 squared. That's a heck of a lot easier than multiplying this out to get terms all the way up to x cubed, taking the derivative of each one on their own, and then putting it back into the brackets there. It's a heck of a lot quicker and a heck of a lot easier. And it's actually really good to use because we can take higher powers or even negative powers and make them much simpler to work with. Let's imagine I give you y equals 1 over 2x plus 6 to the power of 8. 1 over 2x plus 6 to the power of 8. Now, this one would be really quite complex. If we multiplied out the bracket, because there's a power of 8, we then looked at taking each term all on their own, putting them up. Can't be done. But this rule here, writing it in the form y equals ax plus b to the n, and using the derivative of that, actually makes it a lot easier. So if we write it in this form, bring it up, reduce our power to a negative, and get 2x plus 6 to the power of negative 8, we can use the derivative of this in this way to get an answer for this. So remember the derivative was dy by dx equals an bracket ax plus b to the power of n minus 1. So I can use this form to take the derivative of this. So what I can say is fine, so dy by dx equals, bring the power down, negative 8, bracket 2x plus 6. Take 1 off of there, so it goes to the negative 9. And then times it by the value of a, which in this case is the coefficient of x, which is the 2. So that then gives me negative 16 bracket 2x plus 6 to the negative 9. Now I can take this and put it back in this sort of form here, getting rid of the negative power, by writing it as negative 16 over 2x plus 6 to the power of 9. This is a heck of a lot easier and faster than trying to do it any other way, using this relationship and this form of the derivative right here. And it works regardless of whether it's normal powers, whether it's negative powers, or, as in the example I'm about to show you, whether it's a fractional power. So imagine I give you f of x equals the square root of 3x minus 2 to the power of 5. And I want to calculate the derivative of that. Well, I can then do the exact same thing. I want it written in the form ax plus b to the n. So remember, when we're doing it like that, we get rid of any square roots or any big fractions that they're part of. So I rewrite it as 3x minus 2 to the power of 5 over 2. Once I've done that for my f of x, I can then straight up just take the derivative and follow the form we just talked about on the previous page. So bring the power down, I get 5 over 2, write my bracket out, 3x minus 2, reduce the power by 1, 5 over 2 goes to 3 over 2, and then times it by the coefficient of a, which remember is the coefficient of the x. So we times it by 3. I can then simplify the whole spiel together, and I get 15 over 2, bracket 3x minus 2 to the power of 3 over 2. And I can get rid of the fractional power in this by going back to this sort of form here, and get 15 over 2 times the square root of 3x minus 2 cubed. It works regardless of the form, but our simple steps to begin with for taking the derivative still follow. We still get rid of any roots, we still get rid of any big fractions are part of and make the powers negative. None of that changes. The only thing that does is our final answer, purely because we've got slightly different numbers, and our functional form up here, the ax plus b to the n, is slightly different from what we had before, but the same general rules apply. Power down, reduce it by 1, times it by a coefficient. It's not complicated. It really isn't.